Welcome. Today, we're going to dive into one of the most fundamental concepts in trigonometry: sine, cosine, and tangent. By the end of this lesson, you will be able to determine the sine, cosine, and tangent of any angle using the unit circle. We'll focus specifically on understanding these functions through the lens of the unit circle, a powerful tool that makes these abstract concepts much more intuitive. Let's begin with a quick review of how we define angles in this context. In the coordinate plane, an angle is in standard position when its vertex is at the origin, the point 0, 0, and one of its rays, called the initial ray, lies along the positive x-axis. So, we start with a point at the origin, draw a ray along the x-axis, that's our initial ray, and then rotate a second ray around the origin. This second ray is called the terminal ray. The angles measure tells us the amount of rotation. Positive angles are measured by rotating counterclockwise from the initial ray. Imagine rotating counterclockwise. That movement defines a positive angle. Conversely, negative angles are measured by rotating clockwise from the initial ray. So, a clockwise rotation gives us a negative angle. An angle can have many different measures while still ending up in the same spot. Angles in standard position that share the same terminal ray are called coterminal angles. They differ by an integer number of full revolutions. A full circle is 360 degrees, or 2 pi radians. This means two angles are coterminal if their difference is a multiple of 360 degrees, or 2 pi radians. So, if we have an angle theta, any angle in the form theta plus or minus n times 360 degrees will be coterminal with it. The same logic applies to radians. For example, an angle of 30 degrees has its terminal ray in the first quadrant. If we rotate another 360 degrees, we end up in the exact same position, giving us a coterminal angle of 390 degrees. Similarly, rotating clockwise by 360 degrees gives us negative 330 degrees, which is also coterminal with 30 degrees. Understanding standard position and coterminal angles is the first step in working with the unit circle. Before we proceed, it's crucial to understand radian measure. While we've just used degrees, radians are the standard unit of angle measurement in higher mathematics, especially calculus. The radian measure of an angle is defined as the ratio of the arc length subtended by the angle to the radius of the circle. The formula is theta equals s over r, where s is the arc length and r is the radius. Imagine a circle. An angle at the center creates an arc along the circle's edge. The length of that arc is s. We divide that by the radius, r, to get the angle in radians. This definition leads to some key conversions. A full circle has a circumference of 2 pi r. So for a full circle, the arc length s is 2 pi r. Using our formula, a full circle's angle in radians is s over r, which is 2 pi r over r. The r's cancel, leaving us with 2 pi. This is a crucial conversion. 360 degrees is equal to 2 pi radians. If 360 degrees is 2 pi radians, then 180 degrees is pi radians. This relationship is the foundation for converting between the two units. Let's work through an example. To convert 45 degrees to radians, we multiply by the conversion factor pi over 180 degrees. The degree symbols cancel, leaving us with 45 pi over 180. Simplifying this fraction gives us pi over 4. So, 45 degrees is the same as pi over 4 radians. Similarly, to convert 7 pi over 6 radians to degrees, we multiply by 180 degrees over pi radians. The pi and radian symbols cancel. We calculate 7 times 180, which is 1260, divided by 6, which gives us 210 degrees. So 7 pi over 6 radians is 210 degrees. Mastering these conversions is essential for our next topic, the unit circle itself. Now, let's introduce our star of the show, the unit circle. The unit circle is simply a circle centered at the origin with a radius of 1. Because its radius is 1, the points where it crosses the axes are 1, 0, 0, 1, minus 1, 0, and 0, minus 1. The beauty of the unit circle comes from a special property. For a unit circle with radius r equals 1, the radian measure formula simplifies. Theta becomes equal to s. This means that for a unit circle, the angle measure in radians is exactly the same as the length of the arc it creates. This gives radians a powerful geometric meaning that degrees don't have. Let's revisit our learning objective. We want to determine sine, cosine, and tangent using the unit circle. To do this, we need to know what to look for. For any angle theta in standard position, its terminal ray will intersect the unit circle at a single point, P. This point P is key. Its coordinates define our trigonometric functions. The coordinates of this point P are x, y. Let's see what x and y represent in terms of trigonometry. Let's begin with cosine. The cosine of an angle theta, written as cos theta, is defined as the x-coordinate of the point P. In other words, the x value on the unit circle is the cosine of the angle. Now for sine. The sine of an angle theta, written as sine and theta, is defined as the y-coordinate of the point P. So, the y value on the unit circle is the sine of the angle. This gives us a simple, powerful relationship. For any angle theta, the point where its terminal ray hits the unit circle is cosine of theta, sine of theta. Let's connect this to our basic SOHCAHTOA definitions. Suppose we draw a right triangle inside the unit circle. The horizontal side has length x, and the vertical side has length y. Since it's a unit circle, the hypotenuse is 1. Remember, CAA, cosine is adjacent over hypotenuse, that's x over 1, which is x. This confirms our definition. And SO, sine is opposite over hypotenuse, that's y over 1, which is y. The unit circle definition is just an extension of SOHCAHTOA to all angles, not just those in a triangle. What does this mean for the values of sine and cosine? Since the point P is on the unit circle, its coordinates must satisfy the circle's equation. That's the Pythagorean identity. It tells us that for any angle theta, the square of its sine plus the square of its cosine always equals 1. Finally, let's talk about tangent. The tangent of an angle theta, written as tan theta, has a few important interpretations. First, it's the slope of the terminal ray. If you think about the slope formula, rise over run, that's y over x. So the tangent of the angle is the y-coordinate divided by the x-coordinate. We can also express tangent in terms of sine and cosine. Since y is sine and x is cosine, tangent is sine divided by cosine. An important consequence of this is that tangent is undefined whenever cosine is 0. Where is cosine 0? At pi over 2, or 90 degrees, and at 3 pi over 2, or 270 degrees. At these angles, the terminal ray is vertical, and the slope is undefined, so the tangent is also undefined. Let's put this into practice and find the exact values for some common angles. Our goal is to determine sine, cosine, and tangent using the unit circle. We'll start with 30 degrees, or pi over 6 radians. Our first task is to find the point P where its terminal ray intersects the unit circle. We'll use a classic technique, a 3-0-6-0-9-0 triangle. Drop a perpendicular from P to the x-axis. This forms a right triangle. Since the angle at the origin is 30 degrees, the other angles must be 60 and 90. The sides of a 3-0-6-0-9-0 triangle are in a specific ratio. The side opposite the 30-degree angle is 1. The side opposite the 60-degree angle is the square root of 3. And the hypotenuse is 2. This is for a triangle that isn't on the unit circle yet. To get our triangle onto the unit circle, we need to make its hypotenuse 1, so we divide every side by 2. This gives us sides of 1/2, square root of 3 over 2, and 1. This is our point P. The horizontal side length is the x-coordinate, and the vertical side length is the y-coordinate. So, P is square root of 3 over 2, 1/2. Remember, cosine is x and sine is y. Therefore, the cosine of pi over 6 is the x-coordinate, square root of 3 over 2, and the sine of pi over 6 is the y-coordinate, 1/2. Now let's find the tangent. Tangent is sine over cosine. So we have 1/2 divided by square root of 3 over 2. The 2's cancel, giving us 1 over square root of 3. To rationalize the denominator, we multiply the top and bottom by square root of 3, which gives us a final answer of square root of 3 over 3. Let's work through another example to solidify the concept of finding values on the unit circle. This time, let's find the sine, cosine, and tangent for 3 pi over 4 radians, which is the same as 135 degrees. First, we draw our angle on the unit circle. 3 pi over 4 is in the second quadrant, between pi over 2 and pi. Now, a powerful technique. We find the reference angle. The reference angle is the acute angle formed by the terminal ray and the x-axis. The full angle is 3 pi over 4, and the angle to the negative x-axis is pi. The difference, pi minus 3 pi over 4, is pi over 4. This means our reference angle is pi over 4, or 45 degrees. We've formed a 4-5-4-5-9-0 triangle. Just like before, we use its side ratios to find the coordinates. The standard 4-5-4-5-9-0 triangle has sides of length 1, 1, and hypotenuse square root of 2. To get it to the unit circle, we divide by square root of 2. Rationalizing the denominators gives us square root of 2 over 2 for both sides. So our triangle's sides are square root of 2 over 2. Now here's the critical step. We're in the second quadrant. The x values in the second quadrant are negative, while the y values are positive. This means the x-coordinate of our point P must be negative. So P is negative square root of 2 over 2, positive square root of 2 over 2. From this we can immediately determine our trig values. Cosine is x, so cos of 3 pi over 4 is negative square root of 2 over 2. Sine is y, so sine of 3 pi over 4 is positive square root of 2 over 2. Finally, the tangent is sine over cosine. We have square root of 2 over 2 divided by negative square root of 2 over 2. This simplifies to negative 1. The key takeaway here is to always remember the signs of x and y in each quadrant. The signs determine the signs of your trigonometric functions. Let's formalize what we just observed about the signs of sine, cosine, and tangent. Since cos theta is x and sine theta is y, the sign of each function depends entirely on which quadrant the terminal ray lies in. Let's visualize this. In quadrant I, both x and y are positive, so sine and cosine are both positive. Since tangent is y over x, it's also positive. In quadrant 2, x is negative and y is positive. This means cosine is negative, sine is positive, and tangent, positive over negative, is negative. In quadrant 3, both x and y are negative, so cosine is negative and sine is negative. However, tangent is negative over negative, which is positive. And in quadrant IV, x is positive and y is negative. This makes cosine positive, sine negative, and tangent negative. Many people use a mnemonic to remember this pattern. All students take calculus is a popular one. It reminds you which function is positive in each quadrant. All in quadrant I, sine in quadrant 2, tangent in quadrant 3, and cosine in quadrant IV. Using this mnemonic can be very helpful for quickly checking your work. So far, we've focused on finding the point P on the unit circle given an angle. But what if we're given the point P and asked to find the angle? Let's say we have the point P at 1/2, negative square root of 3 over 2. We need to find the angle theta whose terminal ray passes through this point. We can see that the x-coordinate is positive and the y-coordinate is negative. This means our angle must be in quadrant 4. This is our starting point. We know the angle is somewhere in the fourth quadrant. The coordinates also tell us something else. Since x is 1/2 and y is negative square root of 3 over 2, we know that cosine of theta equals 1/2 and sine of theta equals negative square root of 3 over 2. Looking at the coordinates, which should now be familiar, suggests that this point comes from a reference angle of pi over 3, or 60 degrees. The values 1/2 and root 3 over 2 are the sides of a 30-60-90 triangle with a hypotenuse of 1. If the hypotenuse is along the y-axis, the angle at the origin would be 60 degrees. Let's form a reference triangle by dropping a perpendicular from P to the x-axis. So, our reference angle is pi over 3. But remember, the reference angle is not the angle theta itself, it's the acute angle with the x-axis. Since our point is in quadrant 4, we find the angle by subtracting the reference angle from a full revolution, 2 pi. The angle theta is 2 pi minus the reference angle. Substituting pi over 3 for our reference angle, we get 2 pi minus pi over 3. Finding a common denominator, this is 6 pi over 3 minus pi over 3, which equals 5 pi over 3. So, the angle corresponding to the point 1/2, negative square root of 3 over 2, is 5 pi over 3. Notice we used two key strategies, identifying the quadrant first and then using the reference angle. Let's work through one more example that involves an angle greater than a full revolution. This will bring us back to the concept of coterminal angles. Let's find the sine and cosine of the angle negative 405 degrees. An angle of negative 405 degrees means we rotate 405 degrees in the clockwise direction. That's more than a full circle. So, we complete one full clockwise revolution, which is negative 360 degrees, and we still have more to go. The remaining rotation is negative 405 minus negative 360, which is negative 45 degrees. This means that the angle negative 405 degrees is coterminal with the angle negative 45 degrees. They end up in the exact same position. Therefore, the point on the unit circle corresponding to minus 405 degrees is the same as the point for minus 45 degrees. So, the sine of negative 405 degrees is equal to the sine of negative 45 degrees, and the cosine of negative 405 degrees is equal to the cosine of negative 45 degrees. Our problem is now much simpler. Find the sine and cosine of negative 45 degrees. A 45-degree angle has the point, square root of 2 over 2, square root of 2 over 2. But our angle is negative 45 degrees. This places us in quadrant IV, where x is positive and y is negative, so we must adjust the sign of the y-coordinate. The correct point for negative 45 degrees is square root of 2 over 2, negative square root of 2 over 2. Now we can find our values. The cosine is the x-coordinate, positive square root of 2 over 2. The sine is the y-coordinate, negative square root of 2 over 2. And because these angles are coterminal, these are also the values for negative 405 degrees. Let's quickly recap what we've accomplished today. We started with the goal of being able to determine sine, cosine, and tangent using the unit circle. We learned about standard position, positive and negative rotations, and coterminal angles. We also reviewed radian measure and saw how it simplifies on the unit circle. The most important takeaway is the unit circle definition. For any angle theta, its terminal ray intersects the unit circle at the point cos theta, sine theta. The tangent is the slope of that ray, which is sine theta over cos theta. This powerful definition allowed us to find exact trigonometric values for various angles by using reference triangles and remembering to account for the signs in different quadrants. While this seems like a lot to remember, the more you visualize the unit circle in practice, the more these concepts will become second nature. Understanding the unit circle is the foundation for all future trigonometric topics you'll encounter. Thank you for watching.